All right. What we're talking about today is the last little piece we're going to add to your notes, okay? So I need you to take your notes out, and we're going to add to, we did the design of the lab, but now we need to talk about a couple of minutes about the solutions that we're making, how we make them, okay? Because in your next lab, you will be making them. Okay, I will not be making them. You'll be deciding the arbitrary amounts. Yes?
Will we be doing a formula right after the design model today?
Not quite. I'll explain when we get to that one. All right, so from yesterday, we decided, based upon what we want to titrate and the target amount of calcium carbonate that is in the Tums tablet, we decided yesterday that we wanted to make 0.40 molar hydrochloric acid. Okay, we're going to add 100 milliliters of that to our two tabs, okay? And what we're going to do with that is we're going to overshoot the equivalence point so that we can drive the reaction by Le Chatelier's principle and find every little piece of calcium carbonate. Find every little piece that's hiding in the tablet. Remember, we got sucrose, we've got food coloring, we've got flavoring. No one just eats chalk except for the kids outside playing harmlessly that you think when you turn around, okay, they're taking hits of calcium carbonate. All right, that's crazy. The calcium they might need. All right, we also discovered that we found out through arbitrary values and again targets amount that we need to make 0.50 molar NaOH. So how do we make these solutions? Okay, well, a titration that we're doing today, a back titration, is only as good as the quality of the standard solutions we start with. If we don't start with very, very accurate solutions, then we're not going to get accurate results. Accuracy is how close we are to a known. All right, so let's start with the hydrochloric acid, okay, and I made it this morning. All right, and so very simply, I started with a stock bottle. That stock bottle was something that I am very sure is correct because I bought it brand new, okay? And what I have in stock, or stock solution of, is hydrochloric acid. And notice the molarity, 3. Now, actually, it's 3.00, okay? So it's got 3 sig figs. So I bought a stock solution, opened it up this morning, okay? The reason why I would only open it up this morning is because hydrochloric acid, okay, is actually a gas dissolved in a liquid. So having the top open, the gas from the liquid is going to leave and your molarity drops. So you got to keep it closed. I just opened this morning. So I'm starting with something that I know definitely from. So to get this solution, because I'm starting with a stock solution that is from a stock known solution, I'm going to use the dilution formula. Okay, so for this one, I'm going to use the dilution formula. And the dilution formula is MV equals MV, and we've used this before. Okay, when we were pouring liquids of individual concentrations together, and the concentrations will change, right? If you add 2 solutions together and the volume changes, you can know that each molarity decreases. So here's what I'm going to do, party people. I'm going to take what I know. I'm going to take my 3.0 molar concentration. That came from a company. It was standardized, meaning they have checked for its accuracy. The question I'm going to do is I'm going to solve for how much of that stock solution that is way too what? Way too concentrated for what I need. Okay? I want my target molarity to be 0.40 molar, and I want to make a certain amount. Now for me, this is going to be different when you make your own lab. For me, I want to make enough for all the labs for the 2 classes. So I'm going to make 1,000 milliliters. Okay? So I'm going to write 1,000 milliliters. Now, for your next lab, you're going to make 100 milliliters. There's a reason for that. You have a 100 milliliter volumetric flask. I'll talk about that. So let's solve for this. 0.4 times 1,000. Hey, that's 40% of 1,000. That's an easy one, right? So that's 400. And then I'm going to divide by essentially 3. And what I get is 133. Let me just check that math. Sometimes I'm just tall.
Mr. Grotsky,
Yeah.
liters instead of milliliters.
You're right. I should have mLs there. Thank you. I appreciate that. Okay. I mean, I could do it in liters, but hey. So 400 divide by 3, and I get, 133.33. So what does this mean? What this means, party people, is I've got to measure 133 milliliters of this stock solution. And somehow I have to make a liter of it. How do I do that? Well, I carefully, painstakingly measure out 100 milliliters of this known stock solution verified by a company. That's why it's expensive. And then I pour it into this flask. This is called a volumetric flask. What's so special, and it's an expensive flask, and you see them out all the time because that's what I use to make solutions. This is a 1 liter or 1,000 milliliter volumetric flask. When you do your own lab, you'll be making a far smaller amount. You'll be using 100 milliliter volumetric flask. What's special about the volumetric flasks, they're made to make solutions. This has a little gray line. I don't know if we can see it. There it is. I don't know if you can see it.
Yeah.
It's got a little gray line. That little gray line makes this flask amazingly expensive. And so what I would do, okay, is I would pour exactly the 133.33 milliliters, spend time making sure that is accurate, pour that in here. Now, the device that I use to pour it in, isn't there some remnants on that device? So I would add water to it and then put this in here to make sure that all the remnants off the glassware I use to measure that is now in here. And then I dilute to what? I've got to dilute to the 1,000 milliliter mark, which is this little tiny gray line. Okay, this little tiny gray line. I got to carefully, painstakingly make sure that it's just on that line, because just on that line is now 1 liter. So in this dilution formula, we solve for how much of the stock solution that's more, they call it a dilution formula because you're figuring out, okay, how much of the more concentrated solution you need to dilute. People mess this up all the time. They know how to solve this easy math, but they don't know what it means. We're going to dilute this to this value. You notice we're starting with 3 molar, and now we're down to 0.4. Okay, and I have that solution made. And of course, today we're going to measure 100 milliliters of it to add to our tabs that are crushed. Okay, so that's an easy one. But there is problems. There is, issues with this method. I got to make sure I get every drop out. I got to measure 133 milliliters of perfectly. Okay, and when I pour from the glassware, every drip's going to come out. I got to make sure that the glassware I used, I clean out with distilled water. I put that in here too. It's not going to matter as long as when I eventually add distilled water, I get to this mark perfectly. Okay? Cover it. Label it. Boom. We have that solution. You'll be doing that if you use a stock solution. In your next lab, you will have stock solutions of acids to do that. The problem is students will do it and leave the top off. And as I'm walking around, I won't be walking around. Lab assistant Ben will find tops off and he'll be screaming at you. He's not really good with kids, okay? All right, put the tops back on. All right. All right. Any case, so that is that. Sodium hydroxide. If you notice, we want 0.5 molar. So party people, and people that want to go to the party just don't know where it is, we're dealing with a salt. Anything that's ionic is in what phase at room temperature? It's a solid. Now, I could have gotten a stock solution of sodium hydroxide, but I'm not going to use it. I'm going to go from the solid, okay? So we have solid sodium hydroxide. So we're going to do this differently, and this should be easy to figure out. So this one, okay, molarity is equal to moles over liter. And for the same reasoning, because I'm doing this for 2 classes, I'm going to make a liter. Make my math simple. So in this case, I'm going to make 1 liter. Now, what's the molarity we want? Well, we want 0.5, 0 molar. So can anyone solve for how many moles I need? It's over 1. Okay?
0.5.
Yes, you're amazing in your area. Just don't get out of it. Okay, so 0.50 moles we'll need. Okay, everyone can see we solve for X. That's a tough one. But you won't have a liter next time. You'll have 100 milliliters. So it'll be 0.1. So next time you do this, you'll be using far smaller concentrations, but I'm making a bigger amount. So all I did was take what? The 0.5 molar that we knew. I wanted to make, this is an arbitrary value, a liter of it. So I solve for the moles that I need. Obviously, making a liter is easy. You'll be making a 0.1 liter because you'll be using a far less smaller. Not every group's going to make a liter for the next lab. That's crazy. Okay, now, I need 0.5 moles of this solid. And of course, it's NaOH. So I got to do a conversion that my Regents kids hate. 1 mole is how many grams? I need a formula mass. Sodium is 23. If you went to the molecular mass party, we know it's sodium hydroxide. It's another fun one. Not as fun as calcium carbonate. Anyone know it?
26.
No. Okay. 40 approximately.
Is that what
I heard
Yes.
26.
No, she said 26. I said.
Oh, I didn't hear it? Okay. But you didn't show up to the party, so anyway, ew, whatever. Okay. This weekend's going to be crazy. We're going to do glucose and KHP. Yes. Okay. You'll be ready for that question and someone asks for it in some part of your life. Never. Okay, but hey, it's good to know. Any case, oh, we can do this math. 0.5 times 40.
20.
Yeah! Okay, so 20.0 grams of NaOH. Now I want to make what? I'm going to make a liter. Okay? Because I'm doing it for entire class. Because I have class. At least period 2, 3, 4. Okay, and today it's 7. Okay, but I'm classy most of the time. Now, I'm going to make a 1 liter solution. So I'm going to carefully measure out sodium hydroxide. Yay. I put the solid carefully in here. I pre-dissolve it with distilled water because the space it takes up as a solid will be different than the space it takes up when it dissolves in the water. So I pre-dissolve it, and then I carefully, painstakingly add distilled water up to the little tiny gray mark, which makes this flask incredibly what? Expensive. Then I shake, 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 okay? And I do what Emma likes to do, the swirl, and we dissolve it, and we have the solution. Now, there is a problem with sodium hydroxide, okay? We know there's a problem with hydrochloric acid. The hydrochloric gas likes to leave from the solution, so you can't leave it open. And also, when you make it from a solution, you got drips and glassware issues you have to clean to make sure every drop gets in there. There's another problem, and a bigger problem with sodium hydroxide. Sodium hydroxide is very much reactive. One thing it does, it will react with the CO2 in the air. It's a scrubber. Those on the humans that go on the Artemis missions, and those that went on the Apollo missions, use scrubbers to get CO2 out of the capsules. CO2 builds up, it's toxic, we know it's a Lewis acid, okay? So what you do is you put a base, you push the air that has CO2 building up from the respiratory gases of humans through cartridges of hydroxides. And what you make is the metal carbonate, and you make water. It's a scrubber. So what's going to happen with solid NaOH is that it's going to get diluted once it's in the air because it's so gosh darn reactive. Now, what makes it reactive? Actually, not as a solid. Not as a solid. What makes it reactive, party people, is this little OH minus. It's so small that it's -1 coulomically attracts things. So much so that most things with a hydroxide are insoluble, right? We talked about that, except for the group 1 ions. It's just too big and their charges are too small. Of course, there's some group 2 ions involved there. So when we have sodium hydroxide in a salt, in this case, in a solid, it's an ionic compound. Don't lose sight of that, unless the iPad's in the way, sorry. My other class doesn't get this lecture. They have to watch me. Okay, sort of on live. Well, I meant live on the video, but any case. So what happens is this hydroxide is going to react with a CO2 when it hits it. Isn't CO2 a Lewis acid? And doesn't it want to accept a pair of electrons? And water is the base, hydroxide's the base. So as this sits in the air for a short amount of time, what happens, my friends, it becomes Na2 carbonate. Okay, and therefore the mass actually goes up. Yet the amount of hydroxide, what? Goes down. So I can't help it. Don't blame me. I tried to make 0.5 molar NaOH, but it's not. No matter how much I spent time in here, sleeping over here last night, measuring, hoping this came out, it just didn't come out to 0.5. You know why? Because it reacts in the air. It gets diluted and something else happens to it. Okay? And I want to show you something. I put a sodium hydroxide pellet in the air today. Okay? I'm going to put it on the screen here. All right? And what I did is sodium hydroxide is also hydroscopic. What that means is not only will it attract CO2, it'll attract water in the air. Water, vapor, or gas will arbitrarily hit this hydroxide, okay? And it'll absorb it into the crystal and make it a kind of wet hydrate. So its mass is what? Increasing, all right? And it'll react with the water a little bit. So it's, again, if the mass increases, its molarity is going to drop, right? Because I think it's a certain mass of hydroxide. So what I'm doing here, party people, is I'm going to put a pellet of sodium hydroxide. They come in like little round little pellets. And I'm going to put it next to the one I've had out cooking the last day. I feel this is like a cooking show. Okay, and I'm going to show you, you're going to tell me which one you think was sitting out overnight here. So here we go. And all of its flavor. Okay, I know it's hard to see. I used to have a black piece of paper here, but any case, this one, that's hard to see probably, but here is my little pellet right here that I just put out. Can you see a shine on it? Yeah, kind of like what? Like what? What? Like what? I was thinking, what did you say?
Like a bowl.
Okay. I'm just thinking, and you're saying something. What about me?
I didn't say anything.
Oh, okay. All right. You know I'm the voted best hair in this school, so why would you go there? What I have left is awesome, okay? Some got like intimidated by the 3 or 4 follicles that are awesome, and they left, okay? Just how it goes. So I got a little gleam here and there. If you notice, this gleam is increasing, isn't it? A little bit. It's absorbing what? Water. It's hydroscopic. It's getting heavier. So when I mass it out, thinking it's what? That 40 grams is all sodium hydroxide. Some of that 40 grams is now what? Water, and also some of it's sodium hydroxide, so it's getting diluted with its mass. This, and it's hard to see, is it kind of melted on itself. I'm gonna let that sit there. Okay, so it actually will dissolve itself by making water, not making water come out, but once it hits it, it stays with it. All right, so we've got problems. So this means I need to talk about one last thing, okay, and then we'll get to the lab. All right, so we said that this lab, yes?
Wait, which one was left out?
This one was left out here.
Okay.
And I know it's hard to see, and if I had I need a darker background. Give me that.
Use Brady's folder.
Thanks.
All right, so if we do that. All right, that does help a little bit. Yeah, that works. Yeah, thank you. Good idea. So that was the tablet. That was the little thing I had out yesterday, and here's today, and you can see it's starting to gleam. And this one's dissolving itself, a lot heavier and a lot bigger. Okay, it's shine. Okay, all right, cool beans. Beans are chill. Now, thank you. Teamwork here. Now, Brady's folder made them. Okay, now, party people. So what we got to do now is, unlike the hydrochloric acid that I'm confident because I just opened the bottle and I paid for the 3 molar concentration that I just diluted carefully, assuming my skills of diluting and that math was correct and measuring. Okay, I'm very confident about this solution. Okay, not so confident about this marker who I went to write and didn't do anything.
Oh!
I'm going home. Okay, I'm going home. Everyone in the video just saw that. I threw that across the room and made it. It happens all the time, not. Okay. All right, so I have to verify this solution. It's called standardization. You probably have heard it. For those
Is
of
that
the
percent yield?
no. But percent yield is a cool thing to randomly say once in a while. Okay, it is. You know, I like turtles and percent yield. Just Emma. Okay. Now, what is standardization? We've got to verify. Hey, it's okay. It's okay. Guys, I want you to calm down. It's okay that we don't know exactly what the sodium hydroxide is, because we're going to figure it out exactly. And we're going to use something called KHP. Okay? Say it with me.
KHP.
I didn't say anything. How can you say it with me? Say it with me.
Say it with
I didn't say anything. You got to say it with me. Okay. Too much fun. Oh, well, it has to end sometime. So, KHP is potassium hydrogen phthalate. It's kind of a weird looking chemical. It's KHCH4, okay, OFO, okay? And what it is this organic compound. For those who are not used to looking at that, these are carbons in the corners. They're living out the H's. This is the carbon backbone. And notice we have a COOH ending. I call that a Q group. Okay, it's an organic acid. And this is an organic acid too, your carboxylic acid group. So what you really have is you've got a C double bonded to an O to an OH. You notice these two O's will pull on that pair of electrons and make the H plus come off. And of course they're connected, okay, to another COOH. And this one's lost already. And it's -1 because it lost the H plus. The K plus ion is attracted to that negative. So what happens is, when we dissolve KHP, what do you think is lost? Yeah, so if I write this here, K, all right, H, CH, H, FO, O, FO. When I dissolve this, it's going to make a spectator. Some of you guys still don't get that. And then we have H, CH, H, FO, O, FO. What's its charge?
negative.
Now, what's really strange is this -1 ion is actually a base. It can still dissociate an H. You say, well, how can it be if it's -1? Because a -1 is what? So kind of far away from the overall what? Molecule. It's like a big molecule, okay? Any case, so this is going to dissociate, okay? Now, it's a weak acid, as I've shown here. Its weak acid is 3.91 times 10 negative 6. I'm going to use KHP to standardize my base solution. I'm going to know the moles of KHP, okay? Now, there's a reason why KHP is beautiful to work with. Number one, it's a weak acid. Do you think it's going to react with anything in the air? No. 2, it's not a solution. There's no drips to make sure I got every little drop like I had with HCl. It's a solid. Second thing, it's got a high molecular mass. When I measure it, if I make a mistake measuring the mass with a big molecular mass, do you think I could overcome that error? If something has a small molecular mass per mole, and you make a small little error, it's a lot of what? Molecules are not counting. For all those reasons, KHP is the standard in standardization of bases. It doesn't react in the air like sodium hydroxide. It's an inactive, inert salt. That's a solid. So I don't need to measure with liquids and dissolve. All I got to do is figure out how many grams in moles. So put this down. How are we going to do this? At some point today, you have to standardize your base before you do your final titration. So what are we going to do in our standardization? Okay, well, we got to verify our base. It's not 0.50. You're going to find today it's like 0.48 or something. But that's what we need to use to back titrate. So in our Biuret of Fun, we're going to put the NaOH. But in this time, we don't know its molarity. Yes, we know it's about 0.5. Okay, here we're going to put KHP. Here's the cool part. Okay, and so how do we design this titration? This is part of your lab. So the question is, how much do I want to actually add? Right? Because I don't want to add 4 liters, okay? How much of the NaOH do I want to add? Well, here's what we know. It's about 0.5 molar, correct? That's my target. I know it's a little bit less. I don't know how much, but we're just kind of setting up the titration. It's 0.5 molar, which equals what? Moles over liters. Okay. All right. Now, here's my question. How much base do you want to deliver to get to the endpoint? We don't want to deliver 1 drop, 1 milliliter. We don't want to have 200 because we have to fill up the Biuret, what, 4 times? What would be a good number? 20. Okay. So if we pick 20, now let's do less. Okay.
10.
How about 10? Okay. Percent yield. All right. So if it's 10, what's my liters?
0.010.
Yeah. Okay. Let's go find how many moles that will deliver if I drop 10 milliliters. I'm sorry for that being the way today. Okay. What's 0.01 times 0.5?
0.05.
How many moles do I got?
It's 0.005.
Okay, good. This is moles of what? NaOH I'm going to deliver, correct? I'm designing my titration. The target is 10. Might be a little more, a little less. You can guess on that one. Okay? Now, check it out, party people. Isn't that have to equal the KHP at equivalence? This sounds ultimately, so this is going to be what? So we need approximately what? 0.005 moles of what? KHP. Okay, here's the cool part. All we got to do is find the grams of that. So we take 0.005 mole of KHP. Now, if you went to the molecular mass party, you already know it's 204.22. Every 1 mole is what? 2240.204. My body's able, but my mind isn't. 22 grams. And let's go find the grams. Okay? Well, I can do this math, I guess. I'm going to mess up. So 0.005 times 204.22. And what do we get? What do we get? Yeah, so we need 1.0 what? 2 grams of KHP. That's cool! All I do is find the grams. I have a little bottle. It's a solid. Measure out that grams. Dissolve it in an arbitrary amount of water. Do you think it matters what the water is? No, because it's about the moles inside. That's what makes KHP so much better. You're not dealing with a solution. So add some what? Arbitrary amount of water, as long as it dissolves. Put a spinner in that. We're going to drop phenolphthalein. Here's the reasoning. This is a what kind of titration is this? This is a strong base, weak acid titration. What's the curve look like? This asymptote is above what? 7, below 7, on 7? Right, so phenolphthalein will be a great indicator to use. Phenol, P-H-T-H-A-L-I-E. Okay, and it goes from what? It's going to go from colorless in acidic solution to pink when it's basic. So we're going to drop 3 drops of phenolphthalein, it'll be colorless. When you start getting close to the equivalence point, the pink color or the fuchsia color, or whatever color you guys tell me it is, because I don't know, is going to start to persist. You slow down drop by drop by drop until 1 drop the color persists just slightly for 30 seconds. If you mess it up, you start again. Okay, so that is the standardization, and that's what you have to do before you back titrate. All right, so that's the explanation of how to make the solutions and explaining why do we standardize? Because my strong base is going to react with what? Everything else. I got to figure out what it is today to know what? Exactly what my tablets are today. All right?